Untuk memulakan pembentang, skop kerja kami melibatkan reka bentuk perkhidmatan bangunan bagi kemudahan kerajaan 4 tingkat yang mempunyai zon fungsi yang sangat spesifik. Bangunan ini merangkumi lobi awam di tingkat bawah, pejabat pentadbiran di tingkat 1, hub servis di tingkat 2 dan Dewan Serbaguna di tingkat 3. Objektif utama kami adalah untuk mereka bentuk sistem elektrik dan ELV yang selamat, cekap tenaga serta mematuhi sepenuhnya peraturan di Malaysia. Faktor penentu dalam projek ini adalah kebolehpercayaan yang tinggi bagi menjamin keselamatan peralatan IT yang sensitif serta keselamatan orang awam. Seterusnya, kita beralih kepada engineering challenge yang dihadapi. Kami telah diberikan 2 pilihan perunding yang berbeza, iaitu Proposal A dan Proposal B. Proposal A Basic Cost Focus. Cadangan ini menawarkan sistem skim pengagihan LV jejari yang ringkas dengan sistem ALV yang berdiri sendiri. Ia memfokuskan kepada penjimatan kos jangka pendek namun dengan pemantauan yang terhad. Proposal B Integrate Performance. Cadangan ini pula menawarkan sistem pengagihan yang terancang dengan integrasi berasaskan IP serta pemantauan kuasa yang canggih untuk kecemerlangan operasi jangka panjang. Misi utama kami adalah untuk menilai secara kritikal kedua-dua option tersebut bagi memberikan justifikasi teknikal yang kukuh dalam mengesyorkan penyelesaian paling optimal. The Engineering Load Analysis. Berdasarkan misi tersebut, kami telah menganalisis keperluan beban bangunan. Kami mengkategorikan keperluan elektrik kepada 4 kumpulan utama. Yang pertama, General Purpose Loads. Pencahayaan dan soket kuasa di lobi dan pejabat pentadbiran. Yang kedua, Critical atau Sensitive Loads. Fokus utama di aras 2 bilik survey yang memerlukan bekalan kuasa yang sangat stabil tanpa gangguan. Yang ketiga, High Demand Loads. Di aras 3, iaitu Multi-Purpose Hall, sistem perlu mampu menampung lonjakan kuasa secara tiba-tiba ketika acara besar-besaran. Yang keempat, External Loads, termasuk pondok pengawal, pintu gerbang automatik dan lampu kawasan parking. Seterusnya, Distribution and Safety Strategy. Bagi menyokong beban tersebut, kami merangka strategi agihan dan keselamatan. Yang pertama, Hierarchy System. Kami menggunakan susunan berstruktur iaitu MSB ke SSB dan seterusnya ke DB untuk memastikan fault isolation sekiranya berlaku kerosakan. Yang kedua, Flexibility dan masa depan. Kami menyediakan spare capacity bagi memudahkan penektarafan sistem IT atau penambahan peralatan di masa hadapan tanpa perlu merobohkan infrastruktur di bangunan tersebut. Yang ketiga, Compliance. Kepatuhan keselamatan. Setiap pemasangan mematuhi garis panduan Suruhanjaya Tenaga ST dan Akta Bekalan Elektrik dengan penggunaan peranti perlindungan seperti RCCCB dan MCB untuk mencegah risiko kebakaran dan renjatan elektrik.
As for building background, the project entailed the design of electrical and extra low voltage infrastructure for a dedicated 4-story public service facility. This building is designed as a high occupancy government hub requiring robust utility support for both administrative personnel and the general public. And infrastructure strategy, the building utilized a centralized service core layout. This core houses the vertical electrical and mechanical riser, ensuring that power distribution from the ground floor to the third floor follows the shortest possible path, thereby reducing voltage drop and material costs. As for ground floor, with its high volume of public traffic, this is the floor of the building where most public activities take place. It serves as the main entrance to the building, where it got security room, public service counters, queue management system, reception lobby. Security room have a secure centralized hub equipped with a wall-mounted CCTV monitor matrix, communication system, and facility access control panels to manage building safety. Public service counter, a streamlined row of number service bays divided by low profile privacy partitions, It's optimized for fast document processing and clear communication. And so for QMS, touchscreen terminals at the entrance where visitors select their required service department and receive a numbered ticket. And lastly, reception lobby, a bright, high-ceiling lobby with modular tender seating and digital ticket kiosk QMS that guide visitors. As for level 1, it is only used for internal department only, where it got office room, a combination of private and closed executive spaces for confidential management tasks, and an open plan staff area featuring geometric desk cluster and dual monitor workstation to maximize day-to-day term efficiency. Meeting room 1 and 2, a formal space featuring a long modular table with integrated power, ergonomic seating, and a large display for presentations and video conferencing, alongside smaller huddle space designed for quick team syncs. As for level 2, the staff area, this modern open-place office features curved workstation, cluster ergonomic chair, a sleek wood touchdown counter, and floor-to-ceiling window that flood the space with natural light and city views. Records room, a secure climate control achieved utilizing high-density mobile shelving units for organized physical document and log storage room. A server room, a restricted dust-free digital hub equipped with standard equipment racks, precision cooling, UPS backups, and clean agent fire suppression. For level 3, it have multi-purpose hall, a flexible civic auditorium featuring rows of audience seating, a raised presentation stage with a podium, and a minimalist backdrop for community town halls or assemblies. And it got also training room 1, which flexible, a seminar-style classroom featuring rows of modular, forward-facing desks and ergonomic chairs, equipped with a dual projector system and interactive whiteboards for standard group instruction. And for training room 2, a high-tech operation and learning layout configured in a large U-shaped desk formation, anchored by a central multi-screen suspended video wall displaying real-time data analytics.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amir bin Alias, and I will continue for the next part, which is evaluation of installation practices. In this part, it will show a comprehensive assessment of the technical installation practices for the building services. In a 4-story public facility, the layout must consider the safety, maintainability, integration of power, and also the security system. We look at the 3.1 first, low voltage distribution and arrangement. So the low voltage system is very important for the building's operation. Its layout is designed to effectively manage power distribution across all 4 floors. Therefore, there are several things that we need to focus on. The first one is MSB location. The main switch board is usually located on the ground floor in specifically designated electrical room. This location was chosen for its proximity to the TMB substation, intake point, and its accessibility during emergencies. Then DB layout, distribution box layout. Each floor has a unique distribution box in the electrical risers to minimize voltage drop. This arrangement ensures the shortest possible length of final subcircuits, so it will reduce the voltage drops throughout the system. After that is cable routing. There are 2 types of cable routing in this building, which is vertical cable routing and horizontal cable routing. The vertical cable routing is where the power is delivered from the MSB to the upper floor via bus duct or multi-core cables on heavy-duty cable ladders in a protected vertical riser. Meanwhile, the horizontal cable routing, it use the cables are routed through galvanized iron trunking or cable trays that conceal within the cluster ceiling, and it is usually used in office spaces and the multi-purpose hall. And the last one is accessibility and protection. Protective protective devices like MCB and RCCB are positioned at an ergonomic height, approximately 1.5 meter. And for the general areas, we use 30 milliamp for RCCB. For the 3.2 extra low voltage system integration, these systems are designed to enhance the security and communication within the system. One of the extra low voltage system in this building is IP CCTV system. Uh, High resolution IP cameras at key location, for example, like at the entrance, guardhouse, and server room. And this CCTV system utilize power over Ethernet system to simplify installation and it will reduce cost. The next one is access control and intercom. Biometric or card access at the main entrance, and the server room is integrated with the fire alarm control panel for quick evacuation during emergency. After that, public address and queue management. PA system is linked to queue management software for automated voice notification on the ground floor. And the last one is centralized monitoring. The ELV systems are linked to the security management system that are located in the security office on the ground floor. So this configuration will empower the building manager to oversee the entire facility from a single workstation. And for the last part, 3.3, comparative analysis between proposal A and proposal B. There are a few of evaluation criteria that we consider. There is system reliability, integration level, protection and quality, maintenance and monitoring, and future proofing. So starting with the system reliability, proposal A use a simple radial distribution, but a single fault can affect the entire floor. Meanwhile, for the proposal B, it is structured hierarchy with a clear layout from MSB to SSB to DB. So the fault can be isolated locally without a total blackout. The next criteria is integration level. Proposal A system like CCTV and alarm. It is harder to manage. Meanwhile, proposal B, it share a common network and automated response. For example, like fire detection, that triggering door and release automatically. And the next one is protection and power quality. Proposal A provides only basic MCB and RCCB protection with no surge coverage. But Proposal B adds power quality monitoring and surge protection devices, which is essential for safeguarding sensitive IT equipment in the server room. After that, maintenance and monitoring. Proposal A is purely reactive. Problem only discovered after a failure occurs. And the proposal B, it is real-time monitoring that enables predictive maintenance. So it will reduce downtime and long-term operational costs. And the last one is future proofing. For the proposal A, the design of the proposal A will require a major rewiring to accommodate upgrades. But for the proposal B, the modular design of the proposal B with spare capacity makes technology upgrades straightforward and ensure the building stays relevant for the next 50 to 20 years. So from all of these evaluation criteria, proposal B is the recommended solution because it offers a smarter, safer, and more sustainable electrical system for our building.
Next part is supervision and management method. We have inspection, testing and commissioning TNC procedure. The TNC phase is the most critical quality control mechanism in the building life cycle. It ensures that the theoretical design from proposal A or B has been translated into a safe physical reality that complies with the Electricity Regulation 1994 and MSIEC 60364. So we have three phase. First phase is a visual inspection. Before any circuit is energized, a comprehensive visual audit is conducted to identify physical non-conformities. First is conductor identification, verifying that color coding for phase red, yellow, blue or brown, black and gray. For neutral is black or blue, and earth is green or yellow. Is consistent throughout the four-story installation. Next is enclosure integrity, ensuring the main switchboard (MSB) and all distribution board (DB) are IP rated correctly to prevent the ingress of dust or moisture, especially in the ground floor utility room. Next is labeling and schematics. Every outgoing circuit in the DB must be labeled with its destination. For example, level 2 is server room aircon. A finalized single line diagram (SLD) must be laminated and fixed inside each DB door for future maintenance reference. Lastly is termination quality, checking for loose connection, which are a primary cause of electrical fires. Every terminal must be talked to the manufacturer specification. Second phase is mandatory electrical testing. These tests are performed using calibrated instruments to verify the electrical integrity of the wiring. First, we need to continuity testing, which is using a load resistant ohmmeter to ensure that all protective conductor and ring final circuit have a continuous path. A high resistance reading here could lead to a failure in the protective device during a fault. Next, insulation resistant IR testing. Perform using a mega tester at 500 volt DC for a 230 or 400 volt system. The resistance between life to life and life to earth must be at least 1 meter ohms. This verifies that the cable insulation has not been damaged during the pulling process through the conduits. Next is polarity test, a crucial safety check to ensure that all single pole switches and protective devices are installed in the phase conductor, not the neutral. This prevents equipment from remaining live even when switched off. Lastly is earth electrode resistance test is ensuring the building main earth electrode has a resistance low enough, typically below 1 ohm for sensitive electronics like the server room, to safely dissipate dissipate fault current into the ground. Next is phase 3 is a functional commissioning of integrated system. This phase focuses on the behavior of the system under load, particularly the integration described in Proposal B. First is the load balancing, measuring the current on each phase at the MSB to ensure the full-story load is balanced, red, yellow, or blue. Unbalanced load can lead to neutral overheating and energy wastage. Next is ELV integration matrix, testing the logic of the building. For example, the scenario is manual call point or fire alarm is triggered. The required response is the access control system on the level 2 must immediately release all electromagnetic locks, and the PA system must automatically switch to the emergency evacuation message. Lastly is power quality analysis (PQA). For the server room, a PQA meter is used to check for total harmonic distortion (THD). This ensures that the non-linear loads, servers or computers, are not polluting the power supply, which could lead to equipment failure or overheating of the neutral conductor. Next, let's talk about comparative analysis for Proposal A versus Proposal B. In the TNC criteria for complexity of testing, Proposal A is a basic and focus only on safety and individual system function. But for Proposal B is high, require inter-system testing to verify communication between LV and ELV. For engineering verdict, Proposal B ensure a higher level of life safety through automation. Next is testing equipment. Proposal A is a standard meter, which is using multimeter insulation tester. And for Proposal B is an advanced tools, PKE meters, network cable analyzer, and thermal cameras. For engineer verdict, Proposal B use specialized data to verify the health of sensitive server components. Next is time requirement. Proposal A is shorter duration, and systems are tested in isolation. For Proposal B, longer duration. Significant time is needed for software configuration and integration trials. Engineer verdict, the extra time invested in Proposal B reduced the likelihood of system conflict after handover. Lastly, for documentation, Barang G and H, Proposal A is standard compliance form for the Energy Commission (ST), but for Proposal B is comprehensive digital log, IP address maps, and logic response reports. Engineering verdict, Proposal B provides the owner with a digital twin or a clearer map for future troubleshooting. 4.2 is about maintenance planning and contractor coordination. A building lifespan is determined by how well it is maintained after the initial handover. First, the maintenance strategy is preventive maintenance, which is scheduled cleaning of MSB components, checking for loose connection using thermal imaging, and testing backup batteries for ELV system every 6 months. Next is corrective maintenance, a break-fix approach used for non-critical items like general lighting. So next is contractor coordination, which is the project manager must coordinate between the electrical contractor, the ELV specialist, and the IT team for the server room for this four-story building. Coordination ensures that cable trays are not overcrowded and the ELV data cable are kept at a safe distance from LV power cable to prevent electromagnetic interference (EMI). So for the comparative analysis for Proposal A and Proposal B, maintenance efficiency. Under Proposal A, maintenance is largely reactive. which is this can lead to unexpected downtime, which is problematic for a public service building. Next is the power quality monitoring. Proposal P include integrated monitoring. The building manager can see real-time data on voltage drop or harmonic distortion. This allows for predictive maintenance, where components are serviced before they fail, specifically protecting the sensitive hardware in the server room. Lastly is coordination complexity. Proposal B require more intensive coordination during construction due to integrated nature of the IP-based system. However, it simplifies long-term management as all systems can be monitored from a single central workstation.
Now I will talk about societal, health, safety, legal, environmental, and sustainability impacts. In this context, we have impact analysis of the proposed solution, which is the implementation of the electrical and ELV system for story public service building carries significant weight across 5 key pillars. So there is two types of proposal, which is proposal A and proposal B. What is the difference between of them is in the society implication, proposal A fulfills the basic functional requirements, while for proposal B, secure and well informed about their surrounding. For health and safety implication, for the proposal A, the fire alarm will provide automatic unlocking of all doors during an emergency condition, while the proposal B, manual manufacturing one of the security doors increase the likelihood of the trapping of individuals. Legal and regulatory compliance. For proposal A, meets the minimum legal requirements for safety, while the proposal B goes beyond minimums by incorporating surge protection device and advanced earthing for the service room. The next one, for the point 4, environmental impact, which is energy efficiency and resource conservation. For the proposal A, the simple radial system does not take into account which is for total harmonic distortion due to the nonlinear loads and needs specific and inclusive cables for every individual system, resulting in an enormous amount of copper and PVC conduit. For the proposal B, for energy efficiency and resource conservation, is inclusion of power quality management and harmonious filters. Also employs coverage IP network where through power over Ethernet. The building will be able to use only one Cat6 cable to supply both power and data to ELV equipment. The last point is about sustainability, life cycle performance, and future proofing. Proposal A said that should the local authorities need to update or enhance their serve on the second floor and install smart sensor for the third floor hallway within 5 years. By the proposal B, the fact that the proposed infrastructure relies on IP networking and employs the structure cabling approach with available space for upgrading in vertical rises.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haris Zafar bin Taufik. So today I'm going to talk about a recommendation, which is an integrated performance proposal. So after conducting a comprehensive evaluation of the engineering requirements, installation practices, and management methods for this 4-story public building, our team officially recommends Proposal B, the Integrated Performance Focus Scheme. We believe this is the most effective solution for the project's long-term success. So we are going to talk about technical justification. Why choose Proposal B from a technical standpoint? We focus on 3 pillars. First, we have system reliability. Unlike the basic radial approach in Proposal A, Proposal B uses an organized MSB to SSB to DB hierarchy. This ensures that a localized fault like an issue in the third floor multipurpose hall won't disrupt critical operations on the second floor server room. Next, safety integration. We have integrated access control directly with the fire alarm system, a crucial safety upgrade over Proposal A's simple pin-based approach. Third, power quality. Proposal B includes specialized monitoring, which is essential for protecting the sensitive equipment and records housed on the second floor. So on this third slide, we are going to talk about managerial justification. From a management and operational perspective, Proposal B offers superior control and value. So the first thing is preventive maintenance. By separating surveillance and maintenance facilities, the local authority can perform preventive maintenance rather than just reacting to system failures. Next, we have scalability. The IP-based camera network allows us to easily add future equipment without requiring extensive new wiring, unlike the static standalone nature of Proposal A. Lastly, we have accountability. With monitored intrusion alarms in sensitive areas, security teams are instantly notified of unauthorized access, ensuring a high level of site security. So, this is the fourth slide. On this slide, we are going to talk about radar chart comparison on Proposal A and Proposal B. So, this chart provides a clear visual summary of our selection. While Proposal A has the advantage of a lower initial cost, Proposal B significantly outperforms in critical areas like safety, reliability, and future-proofing. When we look at the total cost of ownership for a 4-story building, Proposal B technical and managerial advantages clearly justify the investment. So we are going next to our fifth slide, which is project conclusion and compliance. To conclude, this project has successfully assessed the electrical and ELV needs of the facility, which show that a modern public building requires a comprehensive, high-performing infrastructure. Our design is not only functional but fully compliant with Malaysian law, specifically the Electricity Supply Act 1990 and MSIEC 60364. So this is the sixth slide. The 4 pillars of Proposal B. In summary, Proposal B is the optimal alternative because it guarantees life safety through the integration of fire and access control systems. Second, technical excellence via a structured hierarchy that protects critical hardware. Third, future-proofing through an IP-based structure that supports modular upgrades. And fourth, sustainability by reducing our carbon footprint through power efficient monitoring and PoE technology. This ensures the building remains a safe, sustainable asset for years to come. Thank you.